All right, hi everybody. This is worksheet 11, and we're going to be focusing on the double and single slit and also that thin film interference situation. Pin my video there. Okay, so we kind of have two different scenarios, right? We can either to be talking about the single slit or double slit experiments. Okay. And kind of how I like just very simply remember them is that it's with single, it's alternating orders of bright and dark with that central fringe, that central bright fringe being the brightest and the widest. Okay. And of course, that central is going to be located at the center. And then the bright fringes on either side become progressively dimmer and closer together. And that's a lot easier to see when we consider the I'll write S uh, period S for single slit. And that's kind of easier to see when we do double slit because instead now we'll have kind of a situation that looks something like this. One second, let me draw out it'll look something like this, okay? And then it gets really small on the sorry, it's kind of bad to scale, but it gets really small moving rightwards, okay? And then the dark fringes are always located halfway between the bright fringes and have an intensity of 0, of course, right? It's dark. So that's how like I'm able to kind of look at things and I'll be like, okay, what kind of experiment is this? Okay, it's single slit. And we're looking at the single slit bright spot. Okay, because we're looking at single slit bright, I'll use the equation that I provide for you as max bright. And alternatively, if we're going to be looking at one of those, like we're looking at this position right here on the single slit situation, we know it will be dark there. So we'll be like, okay, single slit, we're looking at the first dark. So, okay, we're going to use the dark equation. And it's kind of confusing, but between each case with the double and single diffraction equations, there's going to be that 1/2. So why are we adding that 1/2 to that order number n? It basically is because we're dealing with both sides of the central maxima. So that 1/2 corrects for that in the calculation. I think that like it's not worth to get too deep into why, but it's just basically that the maximum's at the center, and that's where the top and bottom are equal. And at this point, the waves from the top and the top and the bottom, they interfere constructively. So that means it's a bright spot. And it's not considered a maximum or minimum there, and therefore it's not assigned an ordered number. So that's why we'll call that 0. But then like moving on to over here, we'll call that our first, and that'll be our first dark. And again, because we need to go on either side of this, moving this way or this way, we have to add 1/2 in the cases in which we include the 1/2 to mathematically correct for that. Okay. So that's why it's like the order number plus 1/2. And then, wavelength and non-air substance. That's something that you guys should be used to. And then like, we know that there's these phase changes within the thin film interference. And I just write like what that means. And really what's in parentheses, I think is more valuable. So when we have like this wave, right? And it goes into a medium of higher index of refraction, it undergoes a phase change. And basically it's reflected by 180 degrees. So it like flips over. But that only happens when we go from that low to high. So let's say out here we have air, and over here we have oil 1.5, and then over here we have like water. So we have like, oil spill in the ocean, yikes. When we're dealing with this situation right here, going like this, and then we'll say on the way up, we're going from low to high. So that means, yes, there's a phase change here. However, in this situation, we're like this, there's not a phase change, okay? There's no phase shift. And what does that mean when I say there's a phase shift? So basically we have these constructive and destructive interference patterns, right? Where constructive will like layer on each other and amplify and be something bright and amplify or something like that. And then destructive is actually they're the inverse of each other and they cancel out. So whenever there's a phase change or a pi shift, whatever you want to call it, whenever there's a phase change, the equation you're using flips. So you'll go from constructive to destructive. And then if there's another one, you'll go back. But normally there's only like one. I don't know if I've seen many examples with two. Maybe there's one in the homework actually. Okay, so let me see. Is there anything else I want to say? Yeah, so like depending on the path the light takes with respect to the thin film, you'll either get bright or dark. So like along the x-axis, you'll normally be asked to like find the first dark. And then to determine whether it's constructive or destructive, you have to look at the phase difference between them, right? Okay, so I think that about sums that up. I think it'll be easier to see in an example. Oh, and something cool is with destructive interference, that's how like those noise canceling headphones work. So basically, if you like listen very closely, your headphones will emit a very high-pitched frequency, right? Relative to the sound that's going on in your existence. So let's say like your roommates are being crazy, your headphones will do the inverse wave of the sound wave that's being emitted from your annoying roommates, and it will like since it's the destructive wave, it will cancel it out to zero. So that's kind of cool. That's how that works. Okay, so question one, we have a light of wavelength 680 nanometers. It's a two slit question, and you know it's third order bright fringe, which is some distance we'll call x from the central fringe, which is on a screen that's 2.8 meters away. So we want to know what the separation of the two slits. That's that question. That's that D in the equation. Okay. So I'm looking at this. We already talked about it. We know it's double slit and we're looking at a bright situation. So maybe I should draw it first, actually. We have our two double slit like this. It's being projected on some screen really far away. And then it's easiest to draw like a little triangle here so we can know what we're looking at. So we have the central bright, which is at 0, right? We don't count it. 2, 3, 1, 2, and then 3. We're at the third order. So it goes, remember, it switches every single time. So go bright, dark, or sorry, bright. No. Oh, this is double slit. Yeah, I was like, wait, what? That confused me. That's for single slit. It would be alternating every single time. So this one's bright too, because it's going to be one of the peaks. So bright here and bright here. Okay, and we're told that we're some distance L away from it. So L is going to be equal to that 2.8. And what we're solving for, and we also know X right here. That's that distance between those 2 points. Okay. And X was that 38 millimeters. Okay. And what we're looking for is this distance D, the distance between the two slits. So D sine theta is equal to m lambda. Okay. We're looking for D, so let's get D by itself. Excuse me. Sine theta. Okay. And we don't know what theta is, but we do know how to find it because we know what x and L is equal to. So opposite over adjacent, x over L is going to be equal, and then, plug all that in, and you'll be able to get for the angle theta, which is equal to 0.778 degrees. Okay, now you're able to plug that in. You know we're dealing with third order. We know the wavelength that we're in air. So all you have to do is plug everything in. You solve for D, and D is equal to 1.5 times 10 to the minus 4 meters. See if there's any questions. Okay, so question 2 here, very similar. Again, we're solving for D. So except in this case, we have a single slit. So we just have a slit of a certain distance apart. We know the wavelength and we know how far it is. So really similar setup here. Go like this. We have our single slit. We're solving for what X is equal to. Okay. So between these two, we have that distance D. Like I said, it's easiest to draw a little triangle here to help us kind of break everything down. We have an angle theta. But also, what we're looking for, remember, is between the first, like the central peak, we want to know that distance, right? So we'll call that from this position to this position. Let's call that alpha. And from here to here, let's call this X. So therefore, let's say therefore, alpha is equal to 2x. Okay. So we also know that this distance L, and we know D And we're at the first. Oh yeah, so with these with this situation, basically what this looks like is it alternates that bright and dark, like I said. So over here, it's dark, it's this one like this, like that. So within the center one, this is 0. And this is going to be we'll call this +1 dark, and this is the -1 dark. So that's on both sides of the central peak right there. Okay. So which equation? We're going to use that d sine theta is equal to m lambda. But we need to first find theta. So we can do that because we know what d is. It was given in this question. So theta equals sine inverse m lambda, where m equals 1. And solve for the angle, and you'll get 0.19 degrees. Okay. And then the next thing we need to do is solve for what x is, because we were looking for alpha, and alpha is equal to 2x. So to solve for that x, we can just use that tan function. And now we know what theta is equal to. We just solve for that. We look at the opposite, x, over the adjacent, which is L. So now solve, find x is equal to 0.037. Therefore, alpha is equal to 2x, multiply that guy by 2, equal to 0.0738 meters. Cool. Let's see if there's any questions. All right, so question 3 now. We have a light of a certain wavelength creates a second order bright fringe at 53.2 degrees after passing through a grating. And what is the wavelength of light that creates a first order bright fringe at that of that certain angle? So basically we have two situations, right? We have this slit experiment situation where we have the second and the first order presented. So we can use our equations. D sine theta 1 is equal to m1, and then lambda 1, I should say. And then d sine theta 2 is equal to m2. That's it for the second case there. Theta 2, right? And we'll see that the d is constant here, and that makes sense because it's coming through the same gap, right, of this double slit equation. So therefore, d's are the same. We can set these equal to each other. Now, what does that look like? That will look something like this. They're set equal to each other. So now what we need to do is isolate to one side this lambda 2, because this is the unknown, right? We know that maybe it would have made more sense if like this is the second order situation. So maybe I should have labeled that M2, but don't get confused. And this is that the known wavelength. And then that sine angle is equal to sine 53.1. I have no idea. Like, why am I writing it this way? Okay, so we're dealing with the second order situation. Here, the wavelengths is 632 times 10 to the -9 divided by sine 53.2 is equal to the first order situation, the unknown wavelength divided by sine, and the angle that we're told is 20.6. So now you know to just isolate lambda 2 to one side, solve everything out, and you get 556 nanometers. All right, so now in question 4, we have a light of a certain wavelength sent through two slits. We're dealing with a double slit situation, and it's projected on a screen that is 4 meters away. I'll call L equal to 4. The slit centers are that distance d apart. What are the locations of the first two double slit maxima to the right of the central maxima? So basically, we're looking at the first order situation and the second order situation, right? We're looking at the first two bright there, so the two maxima. And because we have this double slit situation here, it can be 1 and 2, right? But with like a single slit, remember that they everything alternates. So what this looks like is, we have this distance d right here. We're told what that is. We have this L across. We just talked about what that is. we have the first order situation, we'll call that m is equal to 1. And the second order situation, we'll call that m is equal to 2. Okay, therefore, from m1 down, we'll call that equal to x1. And from m2 down, we'll call that equal to x2. Okay, and we have this angle theta right here. Well, theta 1 and theta 2, right? So this would be theta 1, and then from here to here would be theta 2. Okay, so we plugged in enough here. We're dealing with a double slit bright situation. We know our equation we're going to be using, d sine theta is equal to m lambda. Plug in our first situation. Let's get theta to 1 to one side. We're going to be running that sine inverse function, m1 lambda over that d constant. Theta 1 is equal to 2.35 degrees. Okay, we know what the angle is. Therefore, we can solve for x1 because we can run the tan function. So the tan function for theta 1 is equal to x1 over L. So so we plug in theta, we just solve for that. x1 is going to be equal to 0.164 meters. All right, and that's like something I can think of right away is x1 better be smaller than x2, otherwise I mess something up here in my math. Okay, so then we do our next one. Same start. We can run that inverse sine function. The only difference is we're going to be plugging in m2, and it's going to be over that d. Same wavelength also, I should say. Okay, solve for that angle. Theta 2 is equal to 4.7 degrees, bigger than theta 1, as expected. Then we plug it into our tan function. So tan theta 2 is equal to x2 over L. And gosh, second time I did that. X2 is equal to 0.329 meters. All right. All right, so now number 5 here, we have a thin film interference type question. So basically we have a wedge with a certain length, and it's formed between two glass plates of that index of refraction. They're separated on one edge by a small block of height h. The interior of the wedge is filled with a material where the index of refraction is n equals 1.15. Light is normally incident on the wedge from above. What is the x value of the first bright band for the red light of that wavelength, right? So first bright there. So what does that look like? We'll call this Q5. We have a situation where we have two rectangles. Try to not make my drawing look horrible. Okay. And let's label our indexes of refraction. So, and inside here is n equals 1.15. Okay. And we have what we're looking for, I'll do it in orange, is where that first bright band is. We know how long this is. Call that L. We know that there's that block that I said I'm going to call H right here, H. And part of what we're going to need is D1. And the other thing that's very important is to recognize that there's two triangles that we have here. We have this triangle made up of this height D1 and this space X, and this triangle right here, which is made up of this height H and this length L, right? So therefore, the angle that exists right here is the same for the small triangle that it is for the big triangle. So that's going to come into play to help us out later. So I'll call that theta. Okay. So we have this light normal incident comes in here. Actually, it's kind of bad drawing. It should be something like this. It's here, goes up. Phase change here. There we go from that low to high there. And we only have one. So I'll say times 1 phase change. So therefore, we need to switch when you look at which equation we're going to use, right? So I told you that when we're dealing with the bright, we're going to have that constructive situation, but now we're going to do a phase change. We're going to switch by 1. So our equation we're going to use is 2d is equal to m plus 1/2 times the wavelength through the substance we're dealing with here. So what is that substance? Well, the lambda of the substance, say where lambda substance is going to be equal to what it is in air, which is that 600 nanometers, divided by the material, so that 1.15 right there. Okay, so you can now work that all out, and you can solve for d. So we'll say therefore d is going to be equal to the first one, so we can plug in 0 here. So 1/2 plus 0, so just 1/2. That wavelength, so 600 times 10 minus 9 divided by 2 times 1.15. So be mindful that I did that, which is that over there, and then divided by 2 because we have the 2 in front of the d. We're able to solve for d, which is going to be equal to 1.304 times 10 to the minus 7 meters. Okay, so we solve for this d. I don't know why I called it d1, but d. We solve for d. So knowing d, we can now solve for that. Oh, I guess we didn't even need to worry about that theta. But I guess the idea that is important here is that they're the same triangles. So that principle still stands. Now we can solve for what x1 is, which is the unknown, right? We want to know what that is because there's a ratio that exists. We know d over x is going to be equal to h over L. So d over x is equal to h over L. It's a ratio, right? So we can rearrange to solve for x. X is going to be equal to d times L divided by h. Plug in everything because L and h are given. D we just solve for. X comes out to be equal to 3.17 times 10 to the minus 4 meters. Thanks for watching.